I will like to say that this session will be recorded. And also I encourage you to post your questions in chat during the presentations or whenever they come to your mind, but we will have them discussed at the end of all the presentations in the special session dedicated to this. And why not? Please share your thoughts regarding this webinar to Twitter using hashtag NAIADES project at NAIADES project, webinar at NAIADES project. So this being said, I think we can now start. Let me introduce myself. I'm Andreea Paunescu. I'm the project manager on behalf of SIMAVI. SIMAVI is the technical partner supporting one of our pilots, Cubrela, and it is SIMAVI also the work package 8 leader, the integration of NAIADES ecosystem, pilot operation, and validation. The agenda for today will be divided into two sessions and a panel discussion at the end. So in our first session, we will have 3 partners from the NAIADES project presenting. So we'll have AIMEN, who are going to present the artificial intelligence for water quality management. We will speak Juan, Fernández, Montenegro, and Aida, Alvarez, Díez. The second presentation will be held by Marius Jianu from SIMAVI regarding the integrated external user with NAIADES internet services via the marketplace. And from Guardtime, we'll have the third presentation regarding verifiable long-term data integrity in NAIADES. And this presentation will be held by Tuuli Lõhmus. In the second session, we have invited speakers. So we will have Marc Ribalta from EURECAT, who is going to present sewer sediment deposition prediction using machine learning. And at the end, we'll have the panel discussion and wrap-up session. So for the first presentation, let me introduce Juan and Aida, first of all. So Dr. Juan Manuel Fernández, Montenegro, finished his PhD in 2018 at Kingston University, working on Alzheimer's diagnosis, combined computer vision, machine learning, and virtual reality technologies. He obtained a master's science degree in game development from Kingston University in 2014, working on virtual and augmented reality projects. He also obtained his master science degree in telecommunication engineering with a specialization on communication signal from University of Vigo, Spain in 2010. So his professional experience includes a position as researcher at the University of Vigo in 2013, focusing on medical image processing, and now he's currently working at AIMEN as artificial intelligence R&D. I also will introduce Aida Alvarez Díez. She finished her Bachelor's of Science in 2019 at the University of Santiago de Compostela, specializing in cosmology and astronomy. Her final degree project was in analyzing the showers produced by cosmic rays. Now she's currently doing a math degree since 2020, and she's working at AIMEN as artificial intelligence R&D since last year. So Juan, Aida, the floor is yours. Please proceed. Juan, you are muted. Juan, you are muted.
Thank you. I forget that. Thank you, Andrea, for the presentation. So yeah, today we are going to talk about the developments done by AIMEN regarding the during the project NAIADES regarding the services, the artificial intelligence services developed for water quality management. I'm going to start with introduction of those modules. I will present one of them, and my colleagues Aida will present the second one. So, yeah. So a small introduction. I think that everybody is aware of the why water quality is important, and also mentioning that the objective of the European Union water policy is to ensure access to good water quality. Mentioning that most of the causes that produce the deterioration of water quality are basically due to human activities, mentioned there, and also there are environmental effects that also affect that water quality. For that reason, it is important to have a mechanism to detect and monitor water quality, and also smart solutions that allow to be proactive and plan the water quality strategy to avoid this deterioration of water quality. So I'm going to do a small summary about the NAIADES project and where these two water quality components are. So within NAIADES, we are creating an ecosystem of smart solutions for water management at the urban level. And you can see that we have a set of different services, smart services related with water, water demand forecast, failures and leakage detection. And in our case, related to water quality, we have provided two different solutions. One about the water quality forecast, and the second one about dynamical treatment suggestions. So we have created those solutions based on the necessities of the NAIADES pilots. In NAIADES, we have three different pilots, two water utilities, one in Alicante and one in Braila, and a city council in Carús. And for these specific two services, the Carús city was interested in the water quality forecast to be utilized in their fountains to monitor water quality in the fountains. And the second one, the dynamical treatment suggestions, was required by the Braila's water utility, that they want that it will be applied in their drinking water treatment plant. So I'm going to start now with the presentation of the first service. This is the water quality forecast service. That was the purpose of this service is oriented towards solve the problems for the Carús use case. Within the NAIADES is part of the set of services that for water management. And the problem that the city has is that in order to monitor the water quality of the fountains, in these fountains, as you can see in the picture, is used for people to swim and during summer. So they have to send every day, twice a day, staff to measure water quality parameters in order to check that the quality is good enough for people swimming. Taking a bath on it. So in one of the objectives for this, it was to provide an automatic monitoring that reduces the time that the staff has to spend going there. And the second problem that they have is the maintenance practices they have are reactive. So they solve the problems once they detect the water quality has dropped. And this is usually not a good practice because normally it's late. So in that point is where the water quality forecasts come very useful. So to allow them to know how it's going to evolve the water quality, so they can plan in advance and proactively react, not react, but proactively do maintenance and plan the next step to maintain water quality. In this case, for the fountains, they were interested in 7 different parameters to be monitored. Those are pH, temperature, turbidity, redox, chlorates, free chlorine, and total chlorine. So using those parameters, 6 of them are measured using sensors, and one of them, the chlorates, is an estimation based on the other sensors. The solution was provided by another partner from NAIADES, IVATEC, and they have also provided some the sensors to do those measurements. So regarding the solution using artificial intelligence, we need as for all the artificial intelligence solutions data. So for this specific use case, we collect the data during last summer. The fountains are working only during summer period. So last year, we collect this data. We collected the water quality parameters we mentioned before. And since the water quality is highly affected by weather parameters, we also collected wind speed, precipitation, relative humidity, and air temperature. So in our solution, we use this data from the past using the historical values. And we also use the future values of weather. These future values, these weather forecasts, are provided also by another partner from NAIADES. From CERT, they have a module for weather forecast, and we use their outcomes to feed our artificial intelligence algorithm. So the algorithms, the artificial intelligence algorithms that we are using for this solution are recurrent neural networks based on basically on LSTM blocks. We have created 7 different models, 1 per parameter. We follow this strategy because after testing many options, we find out that changing the hyperparameters for each of the water quality parameters provided the best results. So we continue with that strategy. So we have 7 different models that are fed with the data that I saw before. So the water quality parameters and weather parameters from the past and the future weather parameters. Those are flattened in a row of features, so the features vector. And with that information, we train the model and we obtain the following results. So basically, in the table, you can see the error, the root mean square error, and the absolute error also. The results are quite good, excepting some of the attributes, especially the turbidity. We have problems with that parameter. We find out that the sensor saturated a lot during that period of measurements. So for that reason, the results are not so good for that specific parameter. And yeah, this is also other results trying to predict aleatorily some of these parameters. And as you can see, the real and the predictions are quite close, setting the turbidity where it is not working that well. So apart from creating the models with the trained data, we have applied a methodology to retrain these models every year, so they automatically adapt to the data breach that can happen when new data appears at different years. So the model is automatically optimized. So this methodology basically what it does is retrain the models every year to do a retraining of the models, run the predictions with the old models and the retrained ones, and compare their errors. So according to that, the one that has the lower error will be kept as the new model. And this is going to be done every year in order to optimize the model. And finally, I would like to show you how it looks like at this moment in the NAIADES platform. This is the NAIADES HMI. I'm going to share 1 minute. Okay, so in this case, we'll log in with one of the users that has only access to the fountains use case. So this is the screen that they will visualize when they log in into the NAIADES platform for this specific use case, where they can see the current values monitored by the sensors. They will see the forecast. We provide 48 hours forecast every 6 hours. So we provide for each parameter the future predictions, and we also include here the weather forecast provided by CERT, by the other NAIADES partner. So so they can compare how much they were influenced by the weather, since they are quite related. I think that's it from my side. I would like to move the screen to my colleague Aida, that she will present the next use case or the next solution from NAIADES, the dynamical treatment suggestions.
Hi. Well, I'm Aida, and I worked in the dynamical treatment suggestion part of NAIADES. In our case, we wanted to work with Braila's water treatment plant, and water treatment plant is basically a place in which the contaminants from the raw water are removed so that it can be consumed by the public. To be able to do that, to do this, the water is processed, and it's suggested to a lot of treatment processes such as chemicals, sedimentation, aeration. In our case, the processes that we were interested in were two chemical ones. The first one is the coagulation process. In the coagulation, you mix a coagulant into the raw water, and in this case, it was an aluminum coagulant, which is the most frequent one. And what it does, it glues the particles that are floating in the water, making them bigger and heavier. Those masses are called floc, and then the floc is easier to separate from the raw water than the little particles. Now you have bigger ones. And then the other process that we are interested in is the chlorination. And in the chlorination process, you add chlorine to the raw water, and that basically kills the parasite, the bacteria, and the viruses. And you end up with water with chlorine in the end. So our objective in this plant is to first reduce the amount of chemicals they are using, so that it maintains the quality of the water produced, and then suggest treatments from fringe cases. In the case of Aida's water treatment plant, they are located near the Danube River, which has really good water, which means that they usually work with low turbidity low turbidity raw water. But in case that they have some kind of contamination, this program will suggest then a treatment so that that water can't be used and is not wasted. So we ended up using a reinforcement learning method to suggest the treatment. The Saturn says that reinforcement learning problems involve learning what to do or how to map situations to actions so as to maximize a numerical word signal. Moreover, the learner is not told which actions to take, as in many forms of machine learning, but instead must discover which actions yield the most reward by trying them out. So in reinforcement learning, we have different parts. We have an environment, which is the setting. In this case, it will be this little labyrinth. Then you have an agent, it will be the rat, which is the one that has to actually do the actions, is the way that it interacts, the agent, with the environment. In this case, it will be moving through the labyrinth. And then the labyrinth interacts with the agent in given a state, which tells the agent its situation inside the environment. In this case, it will be the location. And then you have the reward, which is the thing that we can't control as the programmer, which will mean what will be actually a successful, which is the success. In this case, it will be taking the little piece of cheese. And in the case of Braille, we ended up deciding to use a really classic approach, which is a multi-arm bandit. So in a multi-arm bandit, you have multiple possible actions. In this case, it will be represented by the bandits inside a casino. Each bandit has a probability distribution which represents the reward. The reward is given by the distribution. It's better. And the agent doesn't know which is the distribution related to each bandit. So the job of the agent is to explore. So he has to try the different bandits so as to have an idea which is the bandit that has the highest reward, and then it has to exploit it, meaning that it has to choose that bandit over and over again so that he maximizes the reward. So how do we apply this to Braille? So the environment was defined by the raw water, and the parameters that we decided to define the raw water were the turbidity, pH, and conductivity. In the end, we ended up with 36 different environments, depending on which turbidity, pH, and conductivity values the water actually took. Then we have the actions. The actions are obviously the amount of coagulant and the amount of chlorine that you put in the water. We have 35 actions, and then the state. The state is going to be determined with the turbidity and the residual chlorine of the water that leaves the facility, the one that has already been treated. And these ones are defined by basically the legality. The different organizations said that the turbidity of the water must be less than 5 NTUs, and the residual chlorine must be between 0.5 and 1 milligrams per liter. So how do we define the reward, which is the thing that is going to tell the agent which are the the good actions. So the reward in the end was decided as a combination of 3 factors. The factor alpha, which is the one that measures if the actions that you have taken produce the desired state, which means a state of water that can actually be used. The beta factor is the amount of product that you have used. This one, you have to minimize it. And then we have to include another factor, which is this gamma one. There is the quality of water after flocculation. Flocculation is a process that happens right before the sedimentation in the filters. So we want to have a little turbidity just before the filters so that the filters don't work as hard and the life of the circle of the filter is higher. That means that you don't have to substitute the filter as frequently because that implies monetary waste. And then you have the fact that alpha is prohibited. This means that if our action, it doesn't matter that use a very little product and that the water after flocculation is good, if it doesn't produce water that can be fed into the public, then we do not take that action into account. And then gamma is extrapolated from tables that hold all the possible combinations of environment and actions. And how do we calculate alpha? Well, this is quite an interesting one. You make a transition matrix. There is one for each environment. And these are basically a probabilistic interpretation. Basically, each cell of the matrix represents the probability that if taken action, in this case the G action, you end up in a state I. So the probabilities over a column are 2, 1, and these and the table for the gamma parameter are loaded into the NAIADES environment. Then here we have a representation of how the matrix works. Here we have for, I think it was the environment 18, the different set of actions taken and how the turbidity was at the end. So as we can see, the action 35 makes turbidity with makes water with lower turbidity, and it's concentrated in a shorter range. That the first action that is associated with lower coagulant, which means that generates turbidity with generates water with higher turbidity, and it's also more spread. And now we kind of decided to use a simulation, basically because we didn't have data from the possible scenarios and combinations, and because we had to interact with the environment. Well, the agent had to interact with the environment so that we can do a multi-arm bandit. And because we needed data to calculate the gamma contribution, because Andreea didn't have the information of the water in the flocculation, we needed to simulate the water treatment plant. Different simulators were considered, and in the end, we decided to use a SIMAVI. So we chose a SIMAVI because it can be integrated into a routine in MATLAB. It's because you can't integrate it in MATLAB. You can also access the code, so you can't edit the code. Also, you had open documentation, and it's also fairly cheap compared to the other programs that were considered. So here I have put the design of Brylas. First you have the raw water, then you have the correlation module, and then you have the flocculation one, a single media filter, and the coordination. And after you had like the drinking water, this will be the designed done in Simulink using STML modules. And as you can see, you can also access all the data through all the different processes. So STML is a simulation program and is a fairly old one, so it has a lot of limitations. The main one that we found it was very bad was the fact that STML cannot simulate correctly at higher turbidities. It starts having this kind of exponential curve, and after I think it's 66 or 67 turbidities of the raw water, it basically cannot simulate water with 100 turbidity in the raw water that enters the treatment plant. It cannot simulate with higher than 57, 58 turbidity. So we cannot have data for those cases. So to resolve that, we decided to do an experiment. So we did this kind of experimental plan that is going to be used first for model validation, so that we can prove that our algorithm and that everything that suggests actions and suggests treatments actually works before it's implemented into the water plant. And then because with this model you can supply cases of higher turbidity, and you can have the laboratory scale data that can be escalated. So it helps us for validation and for those moments in which STML just crashes. And then right now we are validating the model, and then we are improving the model with the data that the laboratory supplies us. And right now I think Juan is going to show us how it's implemented into the NAIADES platform.
Yes, thank you, Aida. So yeah, I would like to show you how it looks like within the NAIADES platform, the NAIADES user interface for this specific use case, the dynamic treatment suggestions for Braille. So for this solution, we have two different user interfaces. The first one monitors, get data from the laboratory mentioned by Aida that we have at AIMEN, where we do we can do the validation of our models. So we can show Braille stuff, how it works even with extreme cases like high turbidity. And so the idea is that in this graph, the historical data recorded is shown to the user, and they can select specific days and see which was the treatment suggested for each of those values. Right now, this HMI is still under development. It's almost done, but there were some problems. So here you have the last values and the last suggested treatments. Right now, the laboratory is working at AIMEN, so these are the values collected by today. Last value here is 12 p.m., but yeah, there should be new ones. And the second user page for this use case is the one dedicated for the Braille drinking water treatment plant. So they are currently measuring the inlet water quality of the drinking water plant in a lab. So they have those values, and the idea is that they can include those values manually in the user interface, send them to NAIADES, and automatically NAIADES will generate a prediction of the treatments, so they can check with the values they collect in the real water treatment plant if it is if it's with what they have planned, and to check if the amount of the dosage is lower, and do the validation also with the data from the real water plant. So that's about the HMI. Sorry, I didn't move this forward, but yeah, just to finish with our presentation, I just want to show you what is required from these modules to be implemented into the NAIADES platform. So NAIADES platform is based on 3 pillars: interoperability, security, and modularity. The interoperability, since NAIADES platform core is based on fireware, so it's we have decided that we should be compatible with fireware data models. So we have created some specific NAIADES data model based on fireware ones. So our solutions are using those data models and communicate to the NAIADES platform, to the core, the fireware context broker, and quantum leap using the NGSI API. Also, it is required for these modules to comply in terms of security and data signature. Security also using a fireware module, KeyRock and Wilma. And regarding data signature, to check the data integrity, we have the components based on blockchain technology provided by our partner Guardtime that they are going to present afterwards. Finally, all of these components should be containerized, and so we are using Docker to provide it to the platform, and so they are easily deployed. And yeah, basically that's it from our part. I think we can proceed to the next one, since the questions are at the end, I think.
Yes. So thank you, Juan. Thank you, Aida, also. So our next presenter speaker, it's my colleague from SIMAVI, Marius Jianu. He's a technical leader in SIMAVI. SIMAVI is one of the most successful software integrators from Central and Eastern Europe. Marius is now involved in several research and development Horizon 2020 projects using artificial intelligence in deep learning for the health domain, circular economy, and other commercial projects. He graduated as an engineer in mechatronics and robotics within the Faculty of Automation, Computers and Electronics in 2011. In the past, he worked in commercial projects as backend and front-end developer. And now he will, and we ask him to share his screen and share his presentation. So Marius, the floor is yours, please. You are muted now.
Can you hear me now?
Yes.
Okay. My name is Marius, as Andreea said. We will present now our component that is called the marketplace. This component is one that represent the, let's say, the broker, the middle point between the external users and some of the NAIADES solution that is available for the public. So basically, for the marketplace, the general aspects would be that it represents a component in which, as I said, external users can see the internal NAIADES services and appear to that text description and the little objective for the NAIADES. They also can see some APIs for integrated with some external applications. That is somehow replacing a Swagger, but we don't want to use a Swagger at this moment. We just want to have one single front end, and from that reason, the marketplace also expose the API in the same UI. Because we intend to let a lot of people to see NAIADES services, we decided that we will apply an internationalization for a lot of languages. Basically are the pilot languages, but of course we have to have an English to be a general one. So related to that, we have English, German, Spanish, French, and of course Romania. Marketplace has basically two parts that are accessed in a public way by the external users, and the second one that represents some private data that could be accessed using an authentication with credentials. For the public part, people can see the list of available NAIADES services and of course a description of that services. Related to the private part, in order to see the API of these services and of course to have the possibility for testing the APIs presented in the same API, they has to be logged in, means create an account and after that log in using the username and the password. Also, the architecture of the marketplace related to accessing the internal NAIADES services is drawing in this picture. So could be seen that external users could access marketplace using an NGINX reverse proxy mechanism. The marketplace component is also deployed in the cloud. Once the user touch the marketplace frontend, the marketplace frontend will call the marketplace backend, and the marketplace backend will send requests to different internal NAIADES services. Identity management for authentication. Of course, all requests will be proxied by the common data validation. Also, the KSI signatures will be validated and the data from internal data management or AI services will be consumed. The idea is we don't want to let external users to consume the NAIADES services directly using let's say, the authorities that our internal pilot can consume. So in order to use that, an NGINX reverse proxy is not enough. We decided that all external requests must be circulated through the marketplace application first. Also, as a technical aspects, the marketplace is composed by two components. We have a separate application that represents the front end of the marketplace, means the UI. This is developed in Angular programming language, of course, with Node.js in the background. We use also Angular materials for drawing elements and tables in marketplace. And the other part is a marketplace backend that is also a different application. He started separately, is written in Java, and of course has a Spring Boot as a framework in background. The communication between marketplace frontend and marketplace backend is established by synchronous communication using HTTP REST protocol. And of course, the communication that's happening under marketplace backend means the communication between marketplace backend and marketplace and NAIADES internal services also use synchronous communication of type HTTP request. As Juan presented before, we are established that all services that runs inside the cloud platform will be containerized using Docker and Docker Compose configuration. So marketplace also will run as a Docker configuration. As we said, the internationalization for the application is in English, German, Spanish, French, and Romanian, and the possibility of changing the language is easily to be touched, and you don't need to be logged in to see the data in other languages. The list of services that Marketplace will publish for the external users are composed by water quality, water demand and consumption, weather prediction, water treatment, water observatory, and leaks and anomaly. Based on that list, this is how Marketplace front end looks like. What we can see here in this picture could be accessed by the external user, even if they are authenticated to the platform or not. We decided to do like that because in order to, let's say, get the curiosity of potential partners that could be integrated with NAIADES solution, we decided that we can let them to see the list of NAIADES services and the short description of them with public access. Of course, they also, in context of the public access, they can see a detailed description of the service, and they can analyze if the service is suitable or not for them, also without authentication. This is an example of weather prediction service description. After that, if some potential, let's say, external users wants to consume some NAIADES services, of course, they need to log in the platform in order to see the API. In this picture, we can see the API description that looks like a Swagger, how they can integrate with an external application, or maybe test it in a Postman if they want, how the request, what is the URL, how the request looks like, what are the parameters, what are the header that they need to add in the request. Also, near the API description that we expose to external user, we have a possibility also in the same front-end page for each of the services in which the external users can test the application. We don't force them to install Postman in computer or to fast develop an application or install another HTTP client. They can simply use the same front end and play around with the parameters described before in order to see the results. This is an example of how a weather prediction service from NAIADES provide a response back due to estimation for the first 6 hours of the same day. Also, regarding the market service APIs and authentication, we have the marketplace authentication and authorization. User must be registered first in the application. We don't want to let external users to access KeyRock front end, as Juan presented before. We just restrict them to use just the marketplace front end. In order to do that, we create a dedicated register form, and the user can create credentials, and we can push that in identity management repository, that credentials. Also, after this process is done successfully, external user can log in the platform using a login form dedicated for the marketplace, the same as before. We avoid to let the user using the identity management KeyRock UI. Also, as I said, even if we design dedicated forms, basically in the background, they authenticate to the platform using the NAIADES KeyRock identity management services. This is how the register form looks like. And of course, after that, the user can log in the platform using the email and the password that they used before. Of course, if they don't want to log in, they can skip the login and see what are the services and the short description of them. This is how the platform informs you that you are logged in the platform. This is the email that you use and are persisted in identity key rock service. So this was all related to the marketplace component.
Okay, thank you very much, Marius. Our next presenter will be Tuuli Lõhmus from Guardtime. Tuuli is a project manager in innovation and research cooperation team in Guardtime, which is an Estonian system engineering company. She has a master's degree in physics from University of Glasgow, and before joining Guardtime, she worked as a radiation safety specialist. Now, as a project manager, she is currently involved in several Horizon 2020 projects like NAIADES and critical chains, as well as an ASA project on using SATCOM system to improve distributed ledger technologies. And now I will kindly ask Tuuli to continue the presentation. Tuuli, the floor is yours, please.
Thank you, Andrea. So, hello everyone. I am Tuuli, and today I will talk about verifiable long-term data integrity in NAIADES. So I will just introduce integrity because it might be a new term and a new concept in the context of water for you. And we'll talk about why checking data integrity is even important and when to do it. We'll then continue to discuss how integrity validation is done in NAIADES project. And I will end with just a short discussion on what we will see in the future about data integrity. So what is integrity? Integrity mechanisms are used to ensure that the product is unchanged and in the original state. For example, in history, letters were usually sealed to protect the integrity of the content. So if you saw an envelope with the seal intact, you would know that the letter inside was protected. And if the seal was open, the integrity of letter might not be the same that the sender intended. And the same with our food, for example. If you look at the tins, they are there to ensure that the integrity of food is protected, so it's hasn't changed from the packaging line. And for packaging, it's easy. We can just look at them and say whether they're good or not. When we talk about data integrity ensures the data consistency throughout its life cycle. So all the data values are unchanged from the point where the data is collected to the point where data is being used. And why we need an integrity mechanism for that is that there are some small changes that are almost impossible to detect when you're just looking at data or when you're analyzing it if you're having very large amounts of data. For example, there are two nearly identical data sets, but in this example, in the visual example, there is just one additional number 7 hiding between number 1s. And when just looking at data, it is nearly impossible to see whether anything has changed. So why do we care about data integrity? We really care about data integrity because data is so important for us right now. There are a lot of predictions, planning, and decisions that are based on data. And if the data has been modified, either maliciously or accidentally during the transport or storing process, the analysis will be faulty and the conclusions you draw from the analysis. For an example of the data modification in the storing process can be that the format of data has changed during the storing process, and maybe all the values were converted to only integer values. So some information was lost in the process, but without knowing this, it's even impossible to know the analysis will be faulty. And data integrity validation is a tool to ensure that the data is unmodified and we can trust the data we have. And checking data integrity is an important step, and this step must be possible in long term without knowing any secrets or passwords for it, because secrets and passwords are very difficult to keep in long term. You can do it for a day or a week maybe, but if you go any further, there will be problems. But integrity checking is not the magical tool for all your data issues. It does not help if the data source, for example, sensor, is producing faulty output. As Juan was talking previously, how one of the sensors was saturated. In this case, we can ensure integrity of the saturation data, but there is no way that integrity checking would change the output. The data that's sent by a faulty sensor or saturated sensor will still be faulty. In the context of NAIADES project, as we have heard before, NAIADES project uses a lot of data for various models and predictions, and in AI and machine learning. So there are water quality treatments and water demand predictions and also weather predictions. And as all of them depend on good quality input, data integrity checking is one of the steps to ensure good quality input, in addition to all the other steps that we must take. And data integrity for all the data sent to NAIADES platform can be verified. We are hoping that by the end of the project, we can say that it is verified, but right now, as it's an ongoing project, we are in the process of ensuring that it is, but right now we can say that it can be verified. So, an introduction to integrity validation in NAIADES. To talk about the specific solution, I will just introduce you to some cryptography. Some of you might already know it, but we'll just go through it once again. The first function that you would like to know is a hash function. So hash function is a one-way function which takes input data and gives a hash value, which is a known length value. It's so for any length of input, you know how long output you're going to get. And very important property of hash function is that it is one way only. Reversing a hash function isn't possible. So if you have only the hash value, you have no information what the input was that was used to generate this. And a significant change in hash value corresponds to a small change in data. So for example, if you only change one value, then you can detect it in hash value and there will be more significant change than just one figure. And those hash functions are used are linked to KSA blockchain, which is a blockchain. It's a private blockchain operated by Guardtime, and this information is used then to get the KSA signature by linking data hashes to KSA blockchain. And the benefits of using KSA signatures are that the signatures are independently verifiable, the signatures do not expire, so KSI signatures can be used for long-term forensic proof. And they overcome technical limitations of other blockchain technologies you might have heard of. So if we talk about how the process we use in NAIADES, so the data is collected and then it is signed at the data source. So when I was talking before that we want to ensure integrity for the whole data lifecycle, the lifecycle begins at the data source. The signed JSON is sent to data model validator, where the model is first validated. And then DMV forwards the signed JSON to KSI verifier for integrity verification. And KSI verifier checks the KSI signature that is added in the first step. For all data, data model and KSI signature are both checked. And any issues for integrity checking are reported to the user of NAIADES platform. So if there are any data integrity issues, the user will be informed of them, and then they can decide how to respond to this information. And just to end, the importance of data is just ever increasing for machine learning, for AI, for all the predictions and models. And right now we see that it is already recognized by critical infrastructure operations, for example, water, like NAIADES project. And there have been energy projects where SCADA systems have used integrity checking to ensure correct operations. And in finances, critical change is one of the projects that looks into financial institutions and their data integrity. But we also feel that the health and space and supply chain are definitely industries that will benefit of data integrity checks in the future. So thank you. That's all from me.
Okay, thank you, Tuuli. With this presentation, we have reached the second session of our webinar. I would like to remind you about addressing the questions in the chat. So at the end, we shall discuss those questions, and at the end of Marc's presentation. So now. We have Marc Ribalta. Marc is a researcher in EURECAT's Applied Artificial Intelligence unit. He holds a computer engineering degree specialized in software engineering from University of Aida, and a computer engineering master specialized in big data, also from the same university. In the past, he had been part in the research group on human-computer interaction and data integration group from the same university, and he worked on integration, query optimization, and visualization of biological data. Currently, he is involved in machine learning projects related to anomaly detection, predictive maintenance, and virtual sensor in the fields of water, agriculture, and automotives. And now he's currently involved in several European innovation projects such as CORE, Water Firewall for Water, and PathoCert. So this being said, Marc, you may proceed with your presentation, please.
Thank you, Andrea. Thank you. So hello, everyone, and thank you for having me here today. Today I will be talking about sewer sediment deposition prediction using machine learning. This work has been done within the scope of the SCO Water project. SCO Water focuses on enhancing the resilience of cities against climate change and urbanization by enabling a water-smart society. Within the project, we have 3 demo cases where we implement different digital solutions to solve urban water challenges. For example, in the case of Amersfoort, we are detecting flash floods. In the Barcelona case, we are improving wastewater management. And then in the Göteborg case, we are improving management of water pollution in the industrial sector. Today, I'm going to focus in the Barcelona case, where we are working with this prediction of the sediment level. So sediment deposition in the sewer system is a common problem for all sewer systems nowadays. The accumulation of sediment basically reduces the volume of water that can be carried by a pipe. And of course, if a pipe was designed to have a certain total amount of volume of water, then the accumulation of sediment, what it makes is that this volume cannot go through it anymore. So what the final problem that we have here is that the pipe gets blocked or has some failure, and of course this produces retentions or flooding in the city. So to ensure that this is not happening, water utilities, local water utilities, use preventive routines and carry preventive routines with cleaning or maintenance over these pipes. And of course, these preventive routines suppose an economic expenditure of millions of euros each year, and for almost all developed countries. And of course, these water utilities, since these preventive routines are really expensive, their main focus is to optimize them and to have only the ones that are needed. So the aim of our solution is to create a predictive maintenance model using machine learning that assist these maintenance routines decision or this tasking for the operators to improve basically the maintenance schedules and therefore reduce the final cost that these routines have. So for our problem, the available data that we have, it's basically of 2 types. First of all, we have the physical sewer pipe features, and then the dynamic features that change over time. Physical sewer pipe features would be the pipe size, the pipe length, the slope of the pipe, the material of the pipe, everything related physically to the pipe. And then dynamic features would be features that are not always the same for the pipe. That would be the rain value between maintenances, the sediment deposition value that changes over time, also the different maintenance routines, if a cleaning has been done or not in a certain time stamp, etc. If we focus here in the middle, we can see the sediment data. And here we can see a plot with different sediment types. And what we can see here is the number of registers that we have for each sediment type. And what we can see here is that the soil and natural waste in sediment is the one that has more data, and therefore this is the one that we are using for our problem. So we are not focusing in other types like the common oils and grease sediment that we also have, but we are focusing in the soil and natural waste. Also here below this plot, we have an example of historical sediment levels. Okay, and here we can see just a common example that we have in one of the sections of our network. And you can see here that this would be 4 timestamps or 4 sediment levels that we have. And here we have an example of on how we identify that a section is being cleaned during the time. You can see here where I have right now my my mouse. You can see here a peak level of sedimentation level. And this is being cleaned because in the same day we have this peak value and a 0 value. So here we label that we have this cleaning. And then we also have another problem, that is the days between maintenance. So for a machine learning algorithm, the best would be to have let's say a stable frequency between these maintenances. That would be, for example, every 30 days we have one maintenance, so the model can see which is the trend behavior or the evolution of this sediment deposition each or every 30 days. But we do not have this because this is really cost consuming. It's really high economically. And so what we have here is a variable days between maintenances that can go from 70 days to a year, more or less. Okay. So this, of course, needs to be also another variable for our model, how many days passed between maintenances. And now to the right, we can also see one of our most important features for our work, which is detection of near sections apart, or the data of the nearer sections apart from the one that we are evaluating right now. So you can see here this really this correlation matrix where in fact the labels cannot be seen. It's a really big correlation matrix. But if we make a little bit of zoom, we can see that the variables that have more correlation between them are actually the sediment level between different pipes or different sections. So pipe 1 will have a lot of correlation with pipe number 2 that can be located near this pipe. It not needs to be adjacent to it, but near the near zone, because social behavior and of course environmental behavior is more or less the same in those zones. So here in the image below, the one I was commenting right now, we can see an example of the network that we are working in. Within the seaward of Barcelona, we are focusing our work in 3 neighborhoods. And this is one of the neighborhoods. And here we can see each point is one of the sections that we are working with. Okay. And for example, if we just put as an example where I have my mouse right now, we would be evaluating this section, but we would use data not only from this section, but also the 5 near sections that are more similar to this one. And we calculated this similar by using a similarity function that basically evaluates the trend of sediment deposition during the time. And if this trend of sediment deposition during the time is similar to the one that we are using, then we are going to use this data of this section also. Okay. And we get a maximum of 5. So we have 5 similar that we are going to use. Now here I'm showing to you the data model that we are using to train our machine learning algorithm. Okay, this is more or less what I said now, but here all the features are shown. So this table shows first of all the name of the feature, then a description, a little description of the feature, and finally the type. The type can be physical or dynamic, as I said. First of all, here you will see different features, which are the physical ones for the sewer section or pipe, which is the pipe section, the perimeter, the length, the pipe width, height, the mean water height, the mean velocity of the water, and the mean flow. And then we have the different, well, the material that this pipe has. Okay, for this mean water velocity and, well, height, velocity, and flow, we are actually calculating it only the mean during the dry season. And this is because we do not have the availability to calculate it in real time, because it needs a network of sensors that calculate it in real time. But what we have here is just a computed value of the velocity and flow, etc., that more or less is similar as to saying, okay, which is the slope of this pipe. Okay. And then we have the dynamic features of this pipe. The first dynamic feature would be the sediment level in 3 different timestamps. So the sediment level that we have right now and the 2 past ones of 2 past maintenance routines. Then the days between the sediment level gathering, the days between maintenances. Then the mean of daily rain between maintenance routines and the standard deviation of daily rain value between maintenance routines. We do this because the mean of daily total rain shows us the amount of rain between maintenance, the accumulated, the total amount of rain between maintenances, and the standard deviation focuses more on telling us when we have high intensity rain periods. And with these two variables, we can focus in these two parts. Then again, as I said before, we also have variables for cleaning, if a cleaning was applied or not. This is Boolean, just a true or a false. And finally, we also have all these same features, but for the 5 near sections. So we need to multiply all these features for each near section that we are going to use. And here, as you can see, if we multiply this by 5, we are going to have a lot of features. And what this means is that we are going to have a problem because, as you can see here on the right, we only have 1900 registers available. And what this means is that we are using a lot of features, but the number of registers that we are using right now, it's not really big. And since it's not really big, the machine learning model usually needs a lot of registers if you give him a lot amount of features. Okay, so our main focus in this work was to try to reduce these variables. One of the exercises that we did was first of all to train an algorithm that's called random forest. I will not enter into it because it makes technically no sense. But we trained this algorithm, and this algorithm can tell us which is the importance of each variable for him or for it. Sorry. And if we focus to the plot, we see the plot at the far left. We see the different variables shown. And we see in the y-axis the importance of each variable. And here the variables that you see or that you can read as value is the sediment deposition for our pipe and the near pipes in the different timestamps. And as you can see, those are the features that are more important for this random forest algorithm. Okay, so the dynamic ones are very important, but if we focus on the physical ones and we make a little zoom here in the middle, we see this plot here in the middle, we can see that all these physical properties, out of all of them, the material features, we can see that some of these features are not important for the model. And in fact, since the value is 0, it means that these features are not even being used by this model. So here what we did, one of our exercises was to just delete all the material features, for example. This is one of them, as I said, but if we delete all of them, we see that we have an increase in importance to all the other physical features. Okay, and as we can see here, before we had a importance of 0.008, but now we have 0.001 as a maximum. Okay, so this increase in importance, it's not really that relevant, but what is relevant is that if we evaluate the predictions done by this random forest algorithm before and after, we have an increase in the algorithm performance by 2%. So what this indicated to us is that we needed to study more complex ways of reducing this huge amount of features, and by reducing them, we are going to obtain better results. So the technique that we are using, it's called autoencoder. Autoencoder, I'm not going to enter a lot, but an autoencoder is a neural network. That's just another algorithm. But this neural network, this architecture of neural network is commonly used to reduce or to filter out the noise of images. Here you can see this, let's say, plot or architecture of an autoencoder where the input is an image with a lot of noise. This image is passed to our autoencoder, and an autoencoder has 3 phases. It has encoding part, the latent space, and the decoding part. The encoding part, what it does is it zips the information of the image. It zips all the information into the latent space, which is the layer here in the middle. This latent space contains all the zipped information, and it passes it to the decoder. This decoder grabs the zipped information and unzips it. And by unzipping it, it produces this output without the noise. And as you can see here, we obtain the same image, but without the noise. Okay, so Our idea here was not to use all these algorithms, but only to use the first part, the encoding part. So we are going to give this algorithm as an input all our information. This information is going to get encoded, zipped, and we are going to extract this information from the middle layer, from the latent space. So we are going to have, let's say, a latent space representation of our, let's say, I think that we had 46 features representing the physical state. And we are going to grab from the latent space 10 features. So this next slide shows you the architecture, the overall architecture that we are using. To the left, you have a more graphical one, and to the right, you have the technical one. Okay. If we focus on the left side, you can see the first input, which is the physical properties of all sewer sections, which are 46 again. We give it to the encoder part of the autoencoder. We give it to the encoder, and then we are going to grab all the information in the latent space, or also called bottleneck. Okay, we are going to have these features reduced into 10, so 10 features representing physical properties, non-linearly, and we are going to join it with the dynamic features. Okay, these dynamic features, as I said before, past sediment, deposition level, cleaning routines, rain impact, and days between routines. All this data is going to be the input of our artificial neural network, which is the final algorithm that we have. And this final algorithm is going to produce the prediction that we are trying to do, which is to predict if the next maintenance routine, which is going to be the sediment deposition level in the next maintenance routine. Okay, now I'm going to explain a little bit more in the next slide. But before, if we go to the right and we enter a little bit to the technical architecture, we are going to see that the autoencoder, as I said, it receives 46 physical features. And it has different layers, which I am not going to comment. But if we have the first layer, it reduces these 46 physical features. It zips it into, or it encodes them into 40. The second one encodes them into 30. And the third one encodes them into 10. And this layer is the bottleneck. Okay. Then this layer, the output of this layer is going to be the one that we join with the dynamic features, and we give it to the final neural network, which is going to perform this final prediction. Okay. Then if you let me go to the results, basically here, what you can see is at the top, you can see a table, and at the bottom, you can see two confusion matrix. Now I'm going to explain them. But first of all, let's go to the table. Here in the table, we can see that we have the column with classification type. So our model is performing 4 types of classification. We have first a classification of, okay, are we going to have more than 5% occupation level within the pipe in, let's say, in 70 days? Remember that we said before that we are predicting between 70 days and 1 year. So we do not know how time has passed. It's one of the features. But so this model, again, is going to predict more than 5% or more than 10 or more than 15 or more than 20. These are Boolean predictions. So it's going to be an output for each classification type. We are going to have the output of true or false, or positive or negative. Okay. Then, as you can see here, for each classification type, we evaluated this model. I'm not going to enter in the methodology that we used. It's called cross-validation, but I'm not going to enter. What I'm going to say is that we used specificity, sensitivity, and accuracy, which all three come from the confusion matrix. Specificity evaluates how the percentage of negative values predicted correctly. By negative, I mean all the times that it's less than, not bigger than. Okay, negative means that it's less than 5 or less than 10 or less than 15 or less than 20. Okay, this is what it means, specificity. Well, or this is what we are trying to evaluate better. And we can see here that our value is always more than 70. And this in machine learning, it's always considered a good. Having more than 70% in a prediction, it's always good. Then if we focus on the sensitivity, sensitivity here evaluates positive registers or positive observations. So by positive, again, means that this bigger than happens. We have this bigger than 5, bigger than 10. Okay, this means that it's positive. And this sensitivity, as you can see, it's even better than or the average value. We do not have this minimum of 74, for example. We only have this minimum of 77. So this is these are very good values. And finally, if we focus on the accuracy evaluates the overall predictions. So it evaluates the percentage of the total observations being predicted correctly. And we can see here that all our predictions are being predicted over 70%. Okay. So as you can see here, we have good predictions, but if you let me go to the confusion matrix, which are a little bit more difficult to interpret, I'm going to explain it really fast. Here we see this is, let's say, just like a table for let's say the 2 rows and 2 columns. Okay, the first row shows all the negative observations, and the second row shows all the positive observations. Okay, then for each column we are going to have the first column shows if our model predicted correctly the predictions of our model, if this model predicted negative, and in the second column if this model predicted positive. Okay, so here if we focus on the first row, we see that our model is out of the total should be like 1200 more or less. Yes, 1200 negative observations. Out of these 1200, we have 800 as true and 300 as false. Okay, so our model predicted incorrectly 300 of these total negative observations. And if we go to the second row, we have a total amount of more or less 700 positives. Okay, positive observations, and our model predicted correctly 600 of them, and 100 of them were predicted incorrectly. Okay, so as you can see here, our model predicts in most of the time correctly these negative observations and positive observations. Okay, these less than and bigger than again. Okay. If we go to the second confusion matrix, this confusion matrix shows us the prediction for bigger than 20%. Okay, the first row shows us negative observations. Here in this case, we have way more, which is 1800. Okay, and we have way more because our data set is imbalanced. Okay, the amount of times that we have more than 20% of our pipe being occupied by a sediment deposition level, it's not really big because of course the maintenance routine want to evade it. Okay, so as I said, out of these 1800 negative observations, 1600 were predicted correctly and 200 were predicted incorrectly. And then if we go to the positive predictions, so predicting that we are going to have more than 20% of sediment deposition, you can see that out of 62, only 5 were predicted incorrectly, and all the others were predicted correctly. So what I want to say with this, and this is just a conclusion that we extract from it, is that our model, it's not always predicting right, of course, but our model is predicting correctly all the times that are going to suppose a risk for our society. So all the times that we are going to have more than 20% of sediment deposition are going to be predicted correctly. Okay. Of course, some of the times these predictions are going to be false positives, and the operators will need to go there and check and do the maintenance routine. But of course, this is going to improve a lot the maintenance scheduling. Okay, and that's all from my side. Thank you very much.
Thank you, Marc. Thank you, everyone, for all your inspired presentation, well detailed, and we really appreciate it, and it was really interesting. I don't see any questions in the chat. If someone wants to ask directly one of the speakers a question, or or maybe just write it in the chat. If not, I'm going to start with the ladies with one question. So I have a question for Tuuli. So Tuuli, what does it mean independently verifiable? How does it work?
Independently verifiable means that for independent verification, the user would only need the data and its corresponding KSA signature. And the signature itself holds the needed data from the originally signed data hash to the publication for integrity calculations and verifications. So the user would have to access the KSA blockchain for verification. And this can be done by the data owner or data holder or anyone else, for example, an auditor. And there is no certificate or certification authority needed for the verification. So the lack of certification authority and verification possible by third party, that's what we mean by independent verification.
Okay, thank you. And now for Aida, regarding the treatment suggestions, is this service optimal? How can it be improved?
One of the things that it could be better if the data that we use for the gamma parameter is one that is a table that is calculated from the simulation data from Estimela. So I would really like to be able to use real data to form that table, and because we have made possible for the model to integrate real data into the transition matrices. But if the transition matrices are updated with the real data, but the table from the gamma parameter is not, I don't think it would work that well. So I would really like that after flocculation data, and also ideally in the laboratory data, also a detector of turbidity could be implemented after flocculation, to have also that data used for the validation. But that cannot be sadly done because we do not have it. The experiment wasn't supposed to have the detector, so now it cannot be implemented. But ideally, I could use that data.
What about the quality forecast service? It is only applicable to the fountains, or where else can it be applicable? It is for you or Juan, whoever wants to answer. Please.
So the algorithm works with the parameters indicated during the presentation, and so it also needs to the weather to be included. So it can be also applied to any similar cases. It could be outside swimming pools. It can be natural sources, rivers, lakes that will suffer from the similar conditions. So the algorithm, as it is automatically retrained, so it can be retrained using data from those places to be improved. So yeah, it could be applied in other different locations.
This is good to know. What about you, Marc, your model? Have you tried using only one model instead of 4 to predict all 4 ingress types?
No, in fact, we are using only one model to predict. So it's the same architecture. We are training with the same architecture, and we are producing 4 models, as you said. But so if we try only to use this architecture to train one model to predict all the 4, we are not going to have enough data. We have tried it, and of course the amount of data that we have is so low that it's not going to learn correctly how to predict all these 5. So this is why we are doing it right now with GIST, with this same architecture and this time.
Now I understand. Marius, regarding the NAIADES HMI and NAIADES marketplace, what are the differences between those two?
Hi. Well, the HMI is the front end of NAIADES solution that is dedicated to internal users, means the pilot ones. But the HMI means the UI of the marketplace is dedicated to external users that are not pilots, but they be considered as a potential future pilots, for example. So in HMI, we have just functionalities strictly dedicated to our three pilots, Carus, Brăila, and Alicante. But the marketplace is for everybody that wants to integrate their solution with NAIADES solution.
And what about the NAIADES services exposed in the marketplace? Are they all exposed or just some of them?
No, in NAIADES marketplace, we expose just some of the services, the main important, but not all the services that are exposed internally for the pilots.
Just some of them. Tuuli, back to you again. I would like you to ask you, how do you describe the scalability and speed of the KSI blockchain compared to other blockchains?
KSI blockchain is a permission blockchain. So there are two types in general, permissioned and permissionless. And KSI blockchain is a permissioned blockchain where the whole network is fine-tuned for the best performance. So our performance is requests per second. And it operates with data hashes. So there is no data storage on the blockchain itself. So it issues KSI signatures as cryptographic proofs. And it gives usually the result commitment time is in the scale of 1 second. And it has massive scalability. So it's billions and billions. So like there is no scalability issue.
Thank you, Tuuli. Marc, I would like to know how did you train the auto encoder and the neural network?
Yeah, so first of all, the way we train is that first of all, we focus only on the autoencoder, and since we are only using the physical features, we train to maximize or to obtain the most optimal architecture out of the autoencoder. So first of all, we train the autoencoder. We use only physical features. We try to have the lowest reconstruction error of this autoencoder. And afterwards, when we have the best autoencoder, we use the neural network, or we train the neural network using this best autoencoder. And this best neural network is evaluated as I showed you in the last slide that I had with all the classification errors.
Okay, thank you, Marc. Juan, could you tell us about the benefits of using IE water quality solutions?
Yeah. In general, the AI solutions are showing that are providing very good results, improving the current ones using traditional methods in most of the areas, not in all of them yet. And so for the water quality, it's also applicable. So it is expected that they are provide better results than traditional methods. And additionally, the artificial intelligence allow to provide better solutions that take into account particularities of each use case, I mean that the particularities of a specific problem can be solved by using artificial intelligence if you have the data to take them into account, of course. Yeah, so apart from that, we have only presented 2 possible solutions for water quality, but there are plenty of more solutions related with that provide solutions to problems that have not been yet solved by any method. Providing measurements for parameters that can be only done very slowly on lab, that it can be provided by artificial intelligence solutions in real time. And so, yeah, there are many good applicabilities for AI solutions for the water quality.
But what about issues? Have you ever encountered issues in implementing those solutions? And what can be work?
Yeah, there are a lot of issues. Basically, the most important or more relevant one is the necessity of that artificial intelligence are highly dependent on good quality data, and that takes time to gather all that information, all that data, sorry. And so I think that is the biggest issue. So how to solve this, it will be to more open data, to share more data. So it is possible to get the amount of data necessary for running this type of artificial intelligence algorithms and to get the highest accuracy of all the solutions.
Marius, I would also like to know if are all the functionalities of marketplace exposed services the same as the internal NAIADES services?
No, in a marketplace, we have some limitations in which we expose it in contrast with what we expose for internal NAIADES services, because we cannot expose to external users all that we expose to the internal ones, because some models needs to be trained especially for what some external users wants to consume. So at least in this moment, it's not possible to offer to external users absolutely all that we expose for the internal ones.
Speaking about external user and internal user,
external
can you
users,
make the difference between them, please?
Yes, the internal users represents the pilot users, means Brăila, Caruja, Alicante, and external ones could be anybody. We don't have control about the external users. Just someone who is interested in NAIADES services and wants to see how they look. So maybe they can integrate in future with their systems.
And these users are related to the water sector or not?
Yes, just to the water sector, strictly what NAIADES provide.
Yes, thank you. Thank you for clarifying this. Regarding Tuuli, the KSI signature, what is considered as a long term for a KSI signature verification?
We consider long term as tens of years.
10 years. Okay, great. Marc, why are we not using variables that indicate special events as a congress or local festival or high tourism periods?
Yeah, so since we do not have high amount of data, and so the model with the amount of variables that we have right now, it's already complex for the model to learn all the relationships between the data. We didn't want to use more specific event data since this specific event data requires of more registers, as I said. So this is for sure, one of the things that we are going to work on in the future, we are going to evaluate if these sort of features are going to be or are important for the actual architecture that we have right now. And of course, we are going to try to include them to the model. Yeah.
But what about the increase of in data and section? Will they benefit to the model?
Yes, yes. So right now, as I said, we are only working with 3 neighborhoods of Barcelona, but if we add or if we have the possibility to add all the neighborhoods into it, we are going to increase, first of all the registers that we have, and also we are going to put more variability into our data, which is a good variability. We are going to have a better shape of how is the behavior of sediment accumulation within the sewer of Barcelona, and this is going to be described by more sections. So this is going to benefit our model.
Okay, so thanks again. Thank you, Marc. And another question for you, Tuuli. What happens with the security of KSI signature-based solution if the hashing algorithm is broken?
Well, it depends on which hashing algorithm property was broken. So this is quite a technical question and a technical answer. So we were speaking about the properties of hashing algorithms, and there were, in addition to determinism, non-reversibility, and diffusion, there are collision resistance, which means that it is hard to find 2 data sets that produce the same hash. And second, pre-image resistance, which means for a specific input, it is difficult to find a different input that produces the same hash. And for either of those cases, it is advised to resign the data if the hashing algorithm is broken with a different hashing algorithm then. And signatures themselves remain verifiable as long as they were created before collision was found. And for the second case, for the second pre-image resistance, the data must be resigned.
Thank you again for your answer and for all your answers. Does someone else have any questions for our speakers today? In the chat, I cannot see any questions, so I assume that we may conclude this webinar here. I will like to thank you all very much for participating, and and I would like to thank the speakers again for their presentation and for what we've learned today. And I will also like to tell you that we really appreciate your thoughts on the webinar to our Twitter, maybe at NAIADES project, and using the hashtag NAIADES webinars. So again, thank you so much for attending this webinar today, and really like to see you in the next ones. Have a great afternoon.
Thank you very much. Have a good day.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you very much.
Thank you. Have a nice day.
Bye.
Bye-bye.
Thank
Have a nice
you.
day.
Bye. Thank you.
Thank you.